Fiber synchronization is, you have your thread synchronization, mutex semaphores. We have the same thing with fibers. You have to have a scheduler. Fiber mutex, instead of blocking, when it can't acquire the fiber mutex, it will yield to the scheduler and let other fibers run. And then when somebody releases that mutex, it then schedules the next person waiting for the mutex. It's very deterministic. It's first in, first out. Whoever fiber mutex, when you try to acquire it, you just get put in a queue. And when you release, it schedules the next person in the queue. Fiber condition is a condition variable for fibers, same thing. Fiber event is the same thing for fibers. An event is not as broadly known. On Windows you have them, and it just allows you to very simply signal the event or to signal to all. And then there's also futures, which a future is, it lets you wait for something to complete. So in other asynchronous I/O frameworks, you'll call the method and then you'll wait for the future. So this future is the same thing that, based on the fibers, allows you to give the future to the asynchronous method, populate the return value, and wait for the future. And you can wait for one future at a time, you can wait for multiple, you can wait for any of the multiple to complete, or wait until all of them complete before you return. So how do you architect with fibers? Big thing is, don't let threading get you down. Really, you shouldn't need to worry about, I need this thread here and this thread here because I'm going to block here and not block here, and I need this queue, and while I'm waiting for that queue, I need a whole thread for that. Don't worry about that. Write them in fibers. Do a logical program flow, and if you need to make it multi-threaded, it's as easy as changing the parameters when you create your worker pool. If you need different worker pools or different I/O managers, or you need to be running on this thread at one point or another thread at another, switch to is super easy. It's a single method call you throw in, and you don't worry about it. Adding threads is easy. If you go with a single-threaded system, so some asynchronous I/O systems, a lot of fiber systems are based on using a single thread. And the benefit of that is you don't have to worry about synchronization because you know exactly where your yield points are. There's no, between this instruction and this instruction, some thread is going to swap in and change the state of my object. You don't have to worry about that with fibers because it's very deterministic. And code is very much simpler with cooperating calls. So cooperating calls is what I call methods that look like they block but don't really block. So a read on a socket, in the normal world you can either do it blocking or non-blocking. But with fibers you can do a cooperative where it looks like it blocks, but underneath it's not blocking. When it would block, it lets other fibers run. So it makes your code look like you're writing in a threaded model and you're blocking, when in reality you have this high performance fiber engine and asynchronous I/O engine underneath. So that's the basics of schedulers. Do we have any questions? I think David has some there. He's getting ready.
Oh, yeah. Yeah, well, so one thing I was interested in was on synchronization.
Uh-huh.
Actually, would you mind going to the slide that you had the animation on, the earlier slide?
Yeah.
So here's my question, is if you want to synchronize between a couple of different fibers, it seems to me you might need to check which thread you're currently on, because if another fiber that you want to synchronize with respect to is on a different thread, aren't you going to need some sort of kernel support? Yeah,
so all of the fiber synchronization, they have a kernel level mutex underneath them. That they lock the kernel mutex so that they're thread safe across multiple threads, and then they check the fiber state to see if anybody's waiting, if they can acquire it. And if they can't, they add themselves to the queue, unlock the kernel mutex, and then yield. So there is kernel level synchronization there, but it's very, very short period of time. Once they've added themselves to the queue and the rest of the time they're waiting for the lock, they're no longer holding the kernel level mutex.
So even if two fibers are synchronizing with respect to each other, do you still need kernel support in that case?
If they're running on the same thread, you don't need it, but Mordor doesn't make that assumption.
Okay.
And it's critical sections on Windows and pthread mutexes on POSIX systems, which means that they don't go to the kernel unless they need to, which makes them very, very fast if there's no lock contention. So it's not very much of a performance hit for a single-threaded system.
So just to make this completely clear, if I'm, say, doing a parallel for each with multiple threads underneath, and each iteration is accessing the same object, then I need to lock my own external critical section.
Yes.
When I do that.
Fiber mutex. Yeah.
Fiber mutex will do that?
Yes. Fiber mutex has it built in, so you don't need to worry about it.
Okay.
Ideally, a parallel for each, as you learn in Intel thread building blocks or GCD, when you want to really parallelize computation, you make each task work on its own, not share state, and then once they're all done, you want to combine them all together, so that there's no lock contention between them.
There was parallel for each and parallel do. What's the difference between those?
Parallel do takes a vector of callable objects and schedules them all at once. Parallel for each takes two iterators and a functor to call with each one of those. Okay. And it has a parallelization parameter that says run at most 4 of these at once or 100 of these at once. Any other questions? Anyone want to see any code?
So one other question I had is about, is there any situation where I/O can block? Because it sounds like what you're saying is you basically are using basically an event-driven I/O manager when you have a situation where you're doing some I/O. I'm just curious if have you found ever any situations where you know the underlying thing you're waiting for isn't compatible with non-blocking I/O?
Yes, definitely. So on POSIX systems, there's very little to no support for doing disk I/O asynchronously. The event readiness mechanisms will always say, yeah, you can read all you want, you can write all you want. It will never block, even though it really does. So that's when you switch to a thread pool that has a pool of threads that are allowed to block. So you have your I/O manager threads that you don't ever want to block. And when you need to do I/O like that, you just switch to a different scheduler. And that's built into the native stream, the fiber streams, or not fiber, file stream is in the constructor. You can pass it optionally a I/O manager and a generic scheduler. And when it can use an I/O manager, it will use an I/O manager. For other operations that it knows will block, it will switch to the scheduler that you passed it.
So it sounds like you're saying that the kinds of objects that you use will sort of give a hint to the scheduler about whether it needs to be in its own thread pool?
Yeah.
In the thread pool? Oh.
Yeah. You pass it in the constructor for the object, and it will switch to a different thread when it needs to. Of course, all the fiber stuff is optional. So a file stream, you can pass it no I/O manager and no scheduler, and then it will operate in a normal blocking manner.